This video will cover edit distance, which is one way to measure the similarity between two words. I'll provide an overview of the topic and discuss the process for computing the minimum edit distance. Then I'll walk through a couple examples, one in which we compute the minimum edit distance between two words, and a follow-up one in which we use that information to find the corresponding alignment between the two words. Finally, I'll go through the algorithm a bit more formally to contextualize what this might look like if you write code to compute the minimum edit distance. There are a variety of ways to measure the similarity between two words or strings in natural language processing. Some of these methods focus on semantic similarity, or how close the two strings are in meaning. Others focus on lexical similarity, or how close the word forms for the strings are to one another. Edit distance is a simple way to compute the latter. Specifically, edit distance computes the number of editing operations that are needed to turn one string into another. The minimum edit distance finds the smallest number of edit operations needed to do this with a given pair of strings. Possible editing operations include insertion, deletion, and substitution. In addition to providing a score indicating the similarity between two strings, computing the minimum edit distance allows you to find the best alignment between them, specifically the sequence of actions needed to turn one string into another in as few steps as possible. We can see what that looks like here, and in this example is also shown in the course textbook. Remember that we have three possible edit operations: insert, delete, and substitute. If we want to convert the string intension into execution, the simplest way to do so is to delete the I, substitute the N for an E, substitute the T for an X, insert a C between the E and the N, and finally substitute an N for a U. If we wanted to, we could also do this at the sentence level to see how to convert one sentence to another in as few steps as possible, or at the phrase level to see how to do so with entities. But the big question that remains is, how do we get there? To find the optimal alignment between two strings, we need to search for a path or sequence of edits from the first string to the second. We'll start out in an initial state, which is word number 1, and we'll work with only our three operators until we reach our goal state, which is word number 2. Our path cost, or the number of operations it takes to get from one word to the other, is what we want to minimize. The thing is, the search space of all edit sequences is really huge, so it'd be impractical to just naively test out all possibilities. Even though we have a lot more compute power now than we had when edit distance was first invented in the 1960s, there are much better things that we can do with our GPUs. A lot of our paths would also just end up at the same state, so there'd be a ton of redundancy. Fortunately, it turns out that to compute the minimum edit distance, we really just need to keep track of the shortest paths. More formally, let's say we have two strings x and y. X is of length n, and y is of length m. We can define the distance at index I of x and j of y as the edit distance between x from index 1 to I and y from index 1 to j. This means that the edit distance between the full strings x and y would be the edit distance between x at index n and y at index m. We can actually solve for this minimum distance using dynamic programming, which we'll see in a few other contexts in this course too. Dynamic programming is table-based, so you compute values at a given point and then store them in a table to use later. The idea behind this is that if you have some string b and it's in the middle of the optimal path from string A to string C, then that optimal path must also include the optimal path from string A to string B. So then we start out by computing our edit distance for the beginning of the two strings, and then successively compute edit distances for points later on in the two strings based on the values we've already computed until we reach the end of the strings. Formally, this process looks like what you see here, and I'll walk through an example of it in practice next. We start out by initializing our distances. So the distance from index I of the first string to a completely empty string is going to be equal to the index itself. For example, the distance from the first character of a string to an empty string would be 1. Then we enter a recurrence relation. So basically, for every index in the first string and every index in the second string, we compute the distance from string number 1 at index I to string number 2 at index j. The distance is going to be equivalent to the minimum of 3 possible values. The first possibility is the distance that we found from the previous index of string number 1 and the current index of string number 2 plus 1. This is an insertion. The second possibility is the distance that we found from the current index of string number 1 to the previous index of string number 2 plus 1. This is a deletion. And then finally, the third possibility is the distance that we found from the previous index of string number 1 and the previous index of string number 2, plus either 2 if the strings are not equal to one another at the current indices, or 0 if they are. This is a substitution. Basically, we'd need to delete one thing in order to insert another. And we're computing Levenshtein distance here, so technically we could change those 1s and 2s to other values and work out this algorithm in exactly the same way, just with different costs if we wanted to. And finally, when we reach the end of both strings, we terminate this process, and we have our minimum edit distance. So now we can work out an example of that process. We'll start out with a completely empty table, and we want to find the minimum edit distance for transforming intention into execution. We can go ahead and fill in the first row. So transforming an empty string into execution would have an edit distance of 0 before the word execution began, 1 at the first letter, 2 at the second letter, and so forth. Likewise, transforming an empty string into intention would have an edit distance of 1 at the first letter, and so on. So now we want to find the minimum edit distance of transforming the first letter in intention into the first letter in execution. Our 3 possibilities are shown here. So our first option is that we can find the distance of transforming an empty string into E plus 1. The cost of transforming an empty string into E was 1, so that's 1 plus 1. So this option would give us a cost of 2. Our second option is to find the distance of transforming an I into an empty string plus 1. The cost of transforming I into an empty string was 1. So that's also 1 plus 1. So this option also gives us a cost of 2. Finally, our third option is to find the distance of transforming an empty string into an empty string, plus either 0 if the two strings are the same at the current indices, or 2 if they aren't. I does not equal E, so we would add 2. So we're adding 0, which was the cost of transforming one empty string into another empty string, and 2, which also gives us a cost of 2. So all 3 options are equally valid in this case. We can select any of them, depending on our preference. I like diagonals, so we'll go ahead and say it's a substitution. So now we have a 2 in this spot. We can continue a bit further and try another example here. In this case, option number 1, where we take the distance of transforming an empty string into EXECUTI and add 1, would result in an 8. Option 2, where we take the distance of transforming an I into EXECUT, would also result in an 8. However, option 3 is a bit different. For option 3, we take the distance of transforming an empty string into EXECUT, and then we look at the current indices to decide what to add. We see that both strings at the current indices are I, so we could add 6 plus 0. This gives us a smaller value than the other two distances, so we'll go with a substitution here. So we can go ahead and follow that process through our whole entire table, and at the end, in the top right corner, we have a minimum edit distance of 8. So that's the smallest possible distance we can achieve using the cost specified to convert intention into execution. So we computed the minimum edit distance, which is useful, but what would be even more useful would be to also know the alignment between the two strings. Fortunately, this is very easy to do. We just maintain a backtrace as we proceed through the algorithm. So every time we move into a new cell, we include a little note indicating how we got there. If it was an insertion, a deletion, or a substitution. Once we reach the end of the table then, we can just trace these little notes backward to figure out what our alignment is. So in this case, if we'd included pointers all along, we'd end up with something like this. Note that we wouldn't have to end up with exactly this, because there are a lot of places where we could have gotten to the same place using multiple strategies, but this is one possibility. So then to find our alignment, we just backtrace using this information. So one possible alignment between these two strings that results in the minimum edit distance is this. Here's the updated algorithm when you include the backtrace. The only thing that is added is a separate variable that holds the pointers for each step. Overall, edit distance is simple to compute, and it gives you a nice measure of the surface level similarity of two strings. Later this semester, we'll also see some ways to compute string similarity at a deeper, more semantic level.